Is by Professor Leong, Chuan, Kwek on Atomtronics towards sensors and devices with ultra-cold atoms and optical lattice.
This late for a talk. I apologize because I have to make a swap, and I have to thank Professor Tarapter for this swap, because he graciously allowed me to speak today because I'm leaving tomorrow morning. Part of the reason being that it's Chinese New Year season in Singapore, and I have to rush back for the celebration. Now, I come from Singapore, and Tony has visited us many, many times in Singapore. In fact, in one of the conference, ICTP, IAS at NTU conference on strongly correlated matter, he was one of the speakers, and I hope you can spot him. That's there. And also, there are many, many other occasions where Tony helped us with organizing conferences in Singapore with good suggestions, including meeting students. And one of those that incidentally he came and doesn't give a talk, but then he was an active member of the school, was when we brought the Lezus School of Physics from the mountain to the island. And that was in 2009, and I have a very blurred picture of him talking to various students. I think I recognized Setiawan, who subsequently gone to Dasama's group, and I think he's now a postdoc somewhere in the United States. Now, let me go into the topic that I'm going to talk about today briefly by talking a little bit from borrowed slides that I got from Charles Clark. And it talk about the internet today being 1.3 million kilometers of submarine fiber optics. There are 2 billion smartphones, or perhaps even more. And there's this vast flow of data that requires high-speed optical communication. And essentially, we solve that with photonics. And of course, the whole idea, of course, is that we could get precise network synchronization through atomic clocks. And so that brings us to some of the dreamlike technologies that we could harness. And one of these dreamlike or blue sky research that we could actually envisage is sort of by replacing our current carrier, which is electrons, with neutral atoms or even neutral ions, whatever. So the carriers, the electrons, are replaced with co-atoms. Semiconductor materials are now replaced with optical lattice, and the electric potential with chemical potential. So that is naive view of the whole thing. Why do we want atoms? Because atoms are identical, they are stable, they are quantum, they are diverse. And why do we bother with atomtronics? It's because of the neutrality of currents. Expect reduced decoherence. Unlike the case of electrons in real materials. We have flexibility with statistics because we can change the type of atoms we use. We have tunable interactions. We can control dimensionality and disorder. We can provide new physics, perhaps. And one of the important things that we have promised to go into this direction is the fact that for a long time, people have looked at mesoscopic physics with real materials, but without a lot of success. So perhaps we could get new devices. And quantum computing, perhaps. So this, I've basically mentioned that earlier on. So optical lattice, of course, are free from dislocation. However, we can also add defects to optical lattice. There's no long-range Coulomb interaction, yet we can invent dipole-dipole forces. There are no phonons, yet we can engineer them. The lattice constant can be tuned, and the potential is exactly known, controllable. It can be switched on and off, modulated, and lattice dimensionality and crystal can be chosen at will. Now let's look roughly at this Atomtronics supposedly timeline. It started, of course, with the Bose-Einstein condensate in the 70s, and the work towards achieving that, starting with trapping, ion cooling and trapping, trapping of neutral atoms, optical lattice. And then, of course, we get, at that time, Bose-Einstein condensation being realized around 2000, in the middle of 1990s, and then followed by atom lasers. In many of this, we get many Nobel Prize winners during those periods, and of course, that doesn't say much about the technology. So we foresee, of course, that atomtronics could be applied to various things ranging from precision measurements all the way to more exotic stuff like topological effects. But what is the workhorse for this new technology? And that is the Bose-Einstein condensate. The Bose-Einstein condensate, of course, I'll skip this one because all of us know what is a Bose-Einstein condensate, because that was. The Atomtronics, of course, one of the first paper to appear in 2007 by Murray Holland's group, in which he explicitly mentioned about Atomtronics in the title. But I believe there was an earlier paper by Fernando Sol who mentioned in the conclusion that there are applications in a field called atomtronics. But I do not know, I have not spoken to Fernando, where he got the idea from. In any case, atomtronic circuits of diodes and transistors followed about 2 years later, same group. And the whole idea, of course, stems from the fact that we look at a one-dimensional model of optical lattice, and that is typically described of a boson in an optical lattice, and that's typically described by a Bose-Hubbard model. We have heard many Hubbard models today, but in this particular case, we're talking about neutral atom, and most of the time for this neutral atom, an effective model, effective Hamiltonian, is just the Bose-Hubbard model. And for the Bose-Hubbard model, the interesting thing, okay, I'll skip the Bose-Hubbard model because all of us know what they are. You have this phase diagram. Now, in the phase diagram, you'll see that if you vary the chemical potential versus the hopping strength, you have a superfluid regime versus a Mott insulator. Now, you can now imagine that the band, this is quite somewhat analogous in semiconductor physics to where the Mott insulator is the band gap and the valence band. So in some sense, this serves as a semiconductor material. Now, however, we need doping to get effective materials. And the way to achieve this in an optical lattice is to somewhat vary the optical lattice. So if you were to vary the optical lattice somewhat with a deeper well, then you get new states that are created, forming what's so-called n-doped material. Or if you raise up the potential of some of the potential well, then you get a p-type material. So this is, in some sense, analogous to conventional silicon materials, where we talk about p and n-type doping near the conduction band or above the valence band. So one can have an N-doped material, and we can have a P-doped material. So according to the logic, we can put them together, and we get an NP material. So this has been shown to be possible, at least theoretically. And of course, for most electronics instrumentations, you need a battery. And a very elementary trivial battery was proposed and experimentally shown by Dana Anderson's group in Gila. And it was a very simple model where you have, effectively, you have a cigar-shaped trap with of Bose-Einstein condensate, and you adiabatically push the condensate to one side. And then you show that this is, in some sense, analogous to a battery with a load. I will not go into detail. Now, so some electronics of this sort can be shown to be possible. And then, of course, some experiments are essential. And this was followed in quite some time ago by an experiment by the Gretchen Campbell group, where they showed that you can actually trap, indeed, you can actually trap a superfluid within optical lattice. In this, not a lattice, but in this case, it's a toroidal shell, a toroidal ring. And you can actually stir this toroidal ring. And this is what actually they did. They construct the an optical colloidal trap, and they load it with Bose-Einstein condensate, and they start to use a light, use a laser beam to stir the ring. And of course, you then can show the basic physics, the theoretical physics behind, of course, is mean field theory with Gross-Pedievsky equation. And effectively, that is quite well described by that equation. And so you can actually experimentally show it being possible that you could stir this toroidal trap. And what is important, perhaps, is that you can also do, when you stir it, of course, you can interfere it with an expanding cloud. So you can have a BEC cloud that is expanding from the center of the ring outwards. And then with the stirred ring, you release it from the trap, and then you see that they form vortices. And these vortices can be measured depending, of course, on the pattern that is created. And what is important is at the point where the stirring occurs, you also can show that there is this phase slip, which plays a very important part in my later discussion. So, so what was shown particularly was that you could manifestly stir Bose-Einstein condensate in a toroidal ring. And what brought us into Atomtronics was back in 2006 or 7. I met up with Luigi Amico, who was from Catania, and he has just published a paper on ring-shaped, a theoretical paper on ring-shaped optical lattice. And he postulates that it is possible in principle to look at loading. But of course, no experiment was done at that time. So I told him that in Singapore, perhaps we could do it. So indeed, the ring trap was not a problem. You can actually put two Laguerre Gauss beam in superposition, and you do form a stationary stack of optical lattice. And this, in fact, was, I think Tony has seen it before in our lab. But at that time, of course, it was not loaded with atom. And actually, until today, we are still trying very hard to load it stably. Of course, there is some progress. although we no longer do it with Leggett-Gauss beam. We now have DMD. So this is the earlier experiment where we showed that we could actually vary the distance between the rings. Now the physics, of course, describing two rings was interesting for us. So we envisaged that there were two rings, an upper ring and a lower ring, both described by Bose-Hubbard model, except that there is this Pearl substitution where we have denoting the stirring in the upper ring and the stirring in the lower ring. You see the phase over of e to the I phi a divided by n. And also the interaction, the hopping between the first ring and the second ring. And so that's a very simple model. And we subsequently show that with these two rings, we could actually realize an effective Hamiltonian that is basically a two-level system comprising of sigma z and sigma x. And of course, we can use this to realize a single qubit gate with the two rings. And moreover, you can also show that in certain limit, you can get a 2 qubit gates. However, there was some difficulties, in fact, with showing gate performance is ideally not superior to superconducting qubit. So we dropped that line of research, and we go on to look at what happened in the case of a single weak link. Now, what is a weak link? The weak link is a point on the optical lattice where, at that point, where the potential is actually higher. So the hopping between those becomes a lot smaller. So we call that a weak link. And with a weak link, we found that essentially this is an atomic squid. And with an atomic squid, now we can think of devices. So we think of replacing the typical superconducting qubit with this atomic squid. In effect, how do we know with this weak link? Of course, with a weak link, there is this possibility that there's persisting current in it, and the current gets reflected off the weak link, and then they form clockwise and anti-clockwise current. But what was more important was we wanted to study whether it's possible to do superposition states, and in some with some approximation, we show that it is possible to see signatures of superposition states through studying the time of flight experiment. What was, in fact, interesting was that this is not very, as long as the student has numerical skill, they could generate beautiful flowery patterns, and this was given to a high school student who eventually end up with big, nice pictures that ends up in a local newspaper. The atomic squid, therefore, allows you this clockwise and anti-clockwise to also form a qubit. Earlier on, we had two layers of current operating between the two rings. And we postulate that there is this possibility for tunneling, and therefore that creates a qubit. But in this particular case, the two qubit is formed from clockwise and anti-clockwise current. And this possibility, of course, is analyzed, and we analyzed that it is indeed possible to look at some Landau-Zener transition. Now, in particular, it's important to know what is really a good qubit. And of course, this this figure of merit, of course, depends really very much on whether the ground state and the first excited state is sufficiently confined so that there is no transition to the next upper level. And so we look at delta E1, which is E1 minus E0, versus delta E2, which is E2 minus E0. And ideally, of course, we expect this number to be small. If this is small, then it is a quality factor for the qubit. If it happens to be exactly half, then it is sort of equidistant. So it must be small in comparison to half. And we did some analysis on that. And we look at the regime where the tunneling versus where the delta E1 is sufficiently small, and show that there are certain regimes where we could operate with certain tunneling and chemical potentials for a small number of sites. There is also some system size scaling, which I'll skip. And of course, with a single weak link, one can, of course, work into more weak links. And that's what we did. And with more weak links, what can we do? We show that it's a versatile DC squid. Now, so let me change gear a bit. And then, of course, Christian Miniatura came along, and he said that in principle, they have shown that with an optical lattice, you can create also many, many little vortices. And with these little rings, and with these little rings, you can form an array of rings. And of course, we were excited about rings because currents in rings can hop, or particles in rings can hop from one ring to another, and try to exploit how this can be used for atomtronics. So, and then one other direction we turned to was actually to follow a paper by Imbri, who recently passed away, and Asbel, where they showed that you could actually, for electronic system, you could actually consider Aharonov-Bohm effect with a magnetic field. And depending, of course, on the magnetic flux, you can get different transmission as regular. So we replace, of course, that particular circuits with a source and a sink, and of course our optical lattice. And the flux that is created is an artificial flux that is created from stirring. And then let's skip that. And then we showed that numerically that you could, in principle, get from the source to the drain. And because it's a closed system, it just oscillates between the two points. So that's with zero flux, and with a 0.5 flux, then you can actually stop the transmission. So plotting against the flux versus the time, you get oscillations that is very much similar to the mesoscopic physics that was predicted in the Israel group. We show also some parity effects, which I'll skip, and some also some coupling effects. You can place the same tricks with boson, anyons, or fermions, and realize different phenomena. Notice that the bosonic currents never gets to zero, this blue one. And depending, of course, on whether it's we plot the flux versus the fractional statistics, and then we show the currents, even for the basic commutation rules, of course, hold. And then in some recent papers, we start to add oscillation, shaking. So we start to add a shaking potential. In what sense? So we still have this, the ring lattice. We have the source lattice, the source Hamiltonian, and we also have the drain Hamiltonian, which is basically a line. And we have the hopping between the source and the ring, and between the ring and the source. And we add one more, which is a time-dependent. I'm supposed to stop after 25 minutes. And we have a time a hopping shaking potential, which is given by that. And with the shaking potential, we have this somewhat similar idea to topological pumping. And we can show that perhaps the rest are not so crucial. We can show that at this junction, what was accidentally discovered was that at this junction, we could engineer, depending on which of these transition points we choose in the landscape, we could engineer an entangled states. So this is 3 at the point B, and C1 and C2 are just the 2 Y junction outlets. We could engineer from 3, say 3 particles coming in, goes to a state in which is 0 particles here, of course, because it's going forward. And then 3 particles either to C1 or 3 particles either to C2, a coherent state of that magnitude, which is, to me, quite nice, because for photonic system, which I've been working a lot for most of the time in quantum information, this state turned out to be terribly difficult. And if the same thing can be approximately achieved with an atomic system, that would be great. At least that was what I thought. And then we tried to see if that could be duplicated on a photonic system with cavity QED system, and it turns out not to be so easy. So you can have 2 species pumping, and the rest I'll skip. You can get it from the preprint archive. And in the last couple of months, well, actually that was done, at least took over a year by the postdoc. We suggest that perhaps we could look back at the toroidal ring instead of the lattice, and then look at a optical channel that is close to the ring. Of course, there are 2 things that we could do. We could shine a beam of atoms, and then look at how it get transferred to the ring. But what we did was that we looked at a field ring, and then look at how it comes out, depending, of course, on the rotation. And so it's not surprising that, in some sense, if we rotate in some way, then if you were to measure this difference in population between the right and left, so this is what the difference is trying to plot, then you find that if this is not rotating, then you don't get any difference between the left and right population. But the moment you start rotating, you can sense whether it's left or right rotating. And so we postulate that this could be serve as a device, and the device is looked to detect these small oscillations that can be can be inflicted into that. Okay, so this is our refrigerator, and it's been building over 7 years, and so far loading is still a big problem. Good loading is still a big problem. We anticipate some success in the next couple of months, but after waiting for 7 years, several months is nothing. If you want to know a little bit more about Atomtronics-enabled quantum technologies, there is a whole workshop that has been generated through that series, and people have come on board. The focus issue will give you some idea. That was for the first workshop. So we're going to organize a 3rd workshop in May. So finally, let me conclude by saying that there are some recent atomtronic device in some sense. We have somewhat, Andrew Daly's groups have somewhat achieved diode. There's Dana Anderson's on the battery. But what is Atomtronics today, of course, is that we could also put some of this Atomtronics device onto space satellite and launch it and see what happens to the physics. And rocket mission, Bose-Einstein condensate has been put in space. We don't know. Unpredictability of such blue sky research is adapted from Sesh's slide, where he talked about the fact that in the 60s we have lasers, 70s we have optical fibers, 50s we have integrated circuit, none of which were actually applied materials. In the 50 integrated circuits is really, before the 50s, it was really non-existent. But now we have the global network, which we mentioned at the beginning. So we never know that all this will blue sky research, what it will lead to. So we are hoping that maybe we could turn this device into a global network. But what is the grand scheme? If it were just replacing electronics with atomtronics, then we would have failed miserably, because electrons are by far the more suitable carrier. And it is, in fact, the grand scheme is, in fact, not to replace electronics, but to explore whether this device could somewhat give rise to new devices in spintronics, in circuit QED, for better sensors, for microfluidics applications, or for quantum simulations. So this is what we expect Atomtronics eventually to do. And let's have a quote from Sesh Ahos, which says that one thing for sure, it's very hard to make prediction about the future, but one thing for sure, without basic research, novel technologies cannot be invented, and the past teaches us that wonderful application always emerge. The same word that Tony used yesterday, serendipitously from blue sky research. I have to acknowledge the whole group of theory and experimentalists whom I've collaborated, and thank you very much. I just took a picture with Tony. I discovered that I don't have a picture with Tony, despite the fact that I've known him for more than nearly 20 years by now. Thank you.
So if there are any quick questions, we can handle it.
Yes, yes.
When you store that Bose-Einstein condensate in a ring, does it stay as a persistent current?
Yes, yes.
For a long time?
Yes, yeah. Not for a long time, but for sufficiently long for the experiment.